Assalamu alaikum, sir. My name is Sanjita Akhtar. Today I will present the solution of my automatic metro crowd management assignment. The project designs a digital system that controls passengers' entry through a metro platform, counts people, raises an alarm if the limit is exceeded, and sends a live voltage signal to the control room. I will describe the answers to all questions one by one, explaining both what the question asked and the full details of my solution. The first question asked me to sketch the block diagram of the automatic metro crowd management system, showing RFID sensors because every passenger must scan a ticket before entering. Its signal is passed to an analog to digital converter to create a clean digital output for logic processing. That output feeds a synchronous counter which tracks the number of passengers on the platform. A finite state machine, FSM, makes a decision about opening or closing the gate based on the counter value and the validity of the ticket. If more than 3 people try to cross together, a 555 timer alarm unit is triggered. Finally, a digital to analog converter converts the passenger count into a smooth analog voltage so the control room can monitor crowd size in real time. This complete chain of blocks, RFID, ADC, counter, FSM alarm, and DAC forms the backbone of the system. Now, the second question asked me to demonstrate how the FSM moves between the states idle, check, open, and close depending on the counter values, and to write the Verilog HDL code. I chose a 2-bit state register because 4 states require only 2 flip-flops. The state codes are idle, check, open, and close. The logic is straightforward. When the gate is idle, a ticket is detected, the machine goes from idle to check. If the ticket is valid and the passenger limit has not been reached, it moves to open so the gate rises. Otherwise, it returns to idle. When the crossing sensor signals that the passenger has cleared the gate, the FSM moves to close and then back to idle to await the next passenger. I wrote the corresponding Verilog HDL code with a synchronous always block for the state register and a combinational always block for the next state logic and outputs. This design provides reliable clock-driven control of the gate. This is my Verilog HDL code according to my solution. Now, about the question 3. It's required a Boolean expression and an AND gate circuit that sounds an alarm if more than 3 passengers cross simultaneously. I labeled the 4 crossing sensors W, X, Y, and Z because the alarm must turn on only when all 4 are active at the same time. The Boolean equation is alarm W, X, Y, Z. Using only NAND gates, I implemented the same 4 input AND function by arranging NANDs in the standard way. When all the W, X, Y, and Z are high, the gate is warm. Whenever 4 people try to cross together, the combined high signals from the sensors drive the NAND network to output a high alarm signal, which immediately activates the 555 timer siren. Alarm signal is connected to the reset pin of 555 timer. When the reset is active, the timer is enabled and the alarm turn on. When the reset is low, reset is 0, the timer disabled, alarm turns off, the alarm does not trigger. This is the difference when the alarm is reset is active and the reset is inactive. Now, the fourth question asked for a 555 timer alarm circuit with a frequency of P5 Hz and a duty cycle of Q% where P and Q are taken from my student ID. From my student ID, I calculated P5 Hz is equals to 185 Hz. Frequency P5 Hz is not within the range, so I chose 400 Hz for my frequency. Then I calculated time period, time high and time low. I obtained a total period of roughly 0.0025 second, a high time of about 2.05 millisecond and a low time of about 0.55 millisecond. Choosing a capacitor of 50 μF gives resistor value of approximately R1 plus R2 approximately 59 ohm, R2 approximately 159 ohm. I drew the full stable circuit and show how the signal from the logic connects to the reset pin, so the siren sound whenever the crowd sensor output is high. So there is my circuit, full stable mode circuit for the question they asked. I used 50 μF capacitor here. This logic connects to the reset pin, so the siren sounds whenever the crowd sensor output is high. Crowd sensor output is high, then the reset pin connects to the logic gate and the siren sounds. So the fifth question asks for the DAC output voltage for passenger count of 5 and 10 using a bit binary weighted DAC with a 5 volt reference. I used bit binary weighted DAC. Anyone can use any DAC. The DAC is 4 bit, B reference 5 volt. Then I use the formula of binary weighted DAC. Then my V out for 5 passenger is 3.125 volt. Where each bit control a resistor branch. For 5 passengers, the binary input is 0101. So the active branches are the D0 and D2. So I use this D0 and D2 in my equation and find the V out, and that is 3.125 volt. For 10 passengers, here the binary code is 0101. When D1 and D3 is activated, V out is findable from 10 passengers. So my V out is for 10 passengers is 6.25 volt. The LSB starts from 0 and D0 and MSB is 1, D3. This result shows that as the number of passengers increases, the DAC output voltage rises proportionally, giving the control room a clear, continuous analog indication of crowd size. So now, the question number 6. The final question asked me to state the limitations of the metro system. I highlighted several important issues. First, the entry limit is fixed. Only 10 passengers may be on the platform and only 20 tickets can be issued each day, and any changes requires reprogramming. If the authority ever wants to change the process or allow more passengers in off days, the program should be installed, which is not a convenient way day-to-day approach. If a sensor falls or two people walk through together, the count may be wrong. Third, there is no backup controller or battery, so a power failure or microcontroller fault will stop the entire gate. Thirdly, the system has limited communication. The DAC they used in their system only a simple analog voltage. It can send detailed data of passengers, so they can't detect the passenger's ID, name, etc. Finally, the RFID tickets can be cloned if proper security have not issues. So someone with copied card might get access. So proper safety measures is necessary for RFID tickets or passes. Future improvement could include redundant sensors, a digital communication link, encrypted RFID cards, and an emergency manual override. In summary, this assignment combines RFID detection, a synchronous counter, a Verilog-based FSM, a NAND gate alarm circuit, a 555 timer, and a binary weighted DAC to create an effective automatic metro crowd management system. Here from the DAC part, I used binary weighted DAC. But DAC has two types, binary weighted DAC and two are ladder DAC. So anyone can use anything. I have described what each question required and how each of my answers, design, drawings, calculation and code meet those requirements. Thank you for listening to my presentation. Assalamu alaikum.